Good. So, hello everyone. Thanks a lot, Willem, for accepting our invitation today. Willem is currently a postdoc at the Institute for Computational Cosmology at Durham University, which is also where he completed his PhD. Willem's main topic of research is neutrino cosmology, and he has done a lot of work on cosmological simulations, particularly with massive neutrinos, and recently decaying dark matter. Willem is a member of the Flamingo simulations project, and is involved with DESI and Euclid. He's also interested in the use of topological data analysis as a complementary probe to traditional two-point statistics. Today, he will present the cosmological neutrino tensions. Willem, please, you can start when you're ready.
Thank you very much for the invitation. And yeah, I'm very happy to talk about this exciting topic of cosmological neutrino tensions. So this talk really comes in two parts about two different tensions. But as you probably know, all the different tensions are tied up with the sum of the neutrino masses. So in the first part, I'll talk about a tension that has probably been lurking in the data for a long time, but is really coming to the fore now. And it's a tension between cosmological constraints on the sum of neutrino masses and the constraints that we get from particularly neutrino oscillation experiments. And so I will set the stage. I will talk about recent findings of negative neutrino masses and the role of dark energy. And then in the second part, I will talk about the S8 tension. So this is the tension between sort of CMB measurements of the amount of clustering and measurements from galaxy clustering and weak lensing. And I will talk about the role of baryonic feedback and why baryonic feedback is actually cosmologically coupled. And this has implications for solutions to the S8 tension. So to set the stage, I will be talking about the standard model neutrinos that we know and love. So there's three of them in three different flavors: the electron neutrino, the muon neutrino, and the tau neutrino. And the neutrinos do something special, which none of the other particles that we know do, which is they oscillate between flavors. And so that tells us that each flavor eigenstate of the neutrinos is really a linear combination of different mass eigenstates. And it's the mass eigenstates that have a definitive mass, and those eigenstates propagate. And the probability of one neutrino transitioning to a neutrino of a different flavor, it depends on the differences in the masses squared. And so from the fact that we see neutrino oscillations, we know that neutrinos have a non-zero mass, but it doesn't tell us the absolute mass scale. And so on the right-hand side here, you can see sort of the masses of different standard model particles and the fact that they span many orders of magnitude. And we don't know the absolute scale of the neutrinos, but they must be many orders of magnitude below all the other fermions. And that's a big question. And we want to explain why neutrinos have mass. And obviously, cosmology has a role to play in this story. So this is the parameter space that we have. It's the sum of the three neutrino masses as a function of the lightest neutrino. From neutrino oscillations, we have these two manifolds where we can be on. We can either be on in the normal mass ordering or in the inverted mass ordering. And depending on which of the two it is, we get a lower bound on the sum of neutrino masses. And interestingly, the sum of neutrino masses is one of the few parameters that we can measure both from cosmology and in the lab. I should just mention there's these two regimes: the degenerate regime, where we have three neutrinos of roughly equal masses, and then the hierarchical regime, where the mass ordering becomes important. But this is the latest constraint from sort of the direct beta decay measurement by the Catron experiment. So this was only announced a few weeks ago. And so the upper bound has gone down by almost a factor of 2 to 0.45 electrovolts for one neutrino. And so that translates to about 1.4 electrovolts for the sun. But with cosmology, we can do better. We get much stronger constraints. So just from the Planck 2018 analysis, we get an upper bound of 0.24 electrovolts, which is about an order of magnitude stronger. But of course, it comes with the assumptions of a particular cosmological model. And by adding different additional cosmological probes, for instance, from the large-scale structure, we can get even stronger constraints. So this is a plot of historical bounds on the neutrino mass since the 1980s. And the red points here are the laboratory measurements using many different techniques, and the same for the black points for the astrophysical or cosmological bounds. And what's interesting is that back in the 1980s, there was this brief period where the two seemed to be in agreement. And now we've gone down by 3 orders of magnitude, and hopefully we will get there again. And get an agreement between cosmology and laboratory measurements. So just this year, we've had some exciting new updates. So I already mentioned the Catherine bound, but we also had the release of the BEO measurements by DESI. And they have really tightened the cosmological constraints. And so you can see here these two black dots in the bottom right of the plot, which are almost at the lower bound for the normal mass ordering, or even pushing below it. And so this is raising some difficult questions for lambda CDM cosmology. Now, as you probably know, the sum of neutrino masses is correlated with many other parameters within the lambda CDM model. And so there's this famous plot from a Planck paper, which I remade here, but it shows you the correlations between the sum of neutrino masses on the horizontal axis, the Hubble constant on the vertical axis, and then the colors indicate sigma 8, or the amplitude of matter clustering. And so these parameters are all correlated. And of course, the tensions in H0 and in sigma 8 therefore also raise questions about the neutrino mass. But these are the constraints that we get from Planck. And if we then add some probe of the expansion history, for instance, from BEO measurements, we can get very tight constraints. So the black contours here show what you get if you add the DESI BEO measurements to Planck, and we get these very tight constraints. And then here, the vertical dotted lines are, again, these lower bounds. So it's 0.06 electrovolts for the normal ordering and 0.1 electrovolts for the inverted ordering. And you can see that the constraints are really pushing these lower bounds. Now, what's been lurking in the data for a long time is that we don't resolve the peak of the posterior distribution of the neutrino mass. So these are the constraints from DESI and CMB. And we see that the mode of this distribution is at 0 electrovolts. And what that means is, and because the data are now so constraining, if we impose a prior from neutrino oscillations, saying that the neutrino mass must be greater than 0.06 or 0.1 EV, it significantly changes our constraints. And so the upper bound changes a lot if you impose these priors. But really, this is telling us that there's some, that there's a tension between the cosmological constraints and the laboratory constraints. So what does this mean? How do we proceed from here? Well, actually, a few years ago, there was already in an SDSS paper, it was shown that if you extrapolate this distribution to negative values, which of course is an unphysical thing, but it's a thought exercise here that we can do. So fitting a Gaussian distribution to this posterior, then you see that the peak of the distribution is in a negative mass range. Recently, there was a paper by Crack et al. Where they did this in a more advanced way by describing the effect of neutrinos on the CMB in terms of A lens. And so A lens is this phenomenological parameter that's basically scaling the CMB lensing potential. And this is because neutrinos suppress the growth of structure, and so they suppress the amount, or they reduce the amount of gravitational lensing, and therefore you can approximately describe the effect of neutrinos in terms of A lens. And doing so, they were able to extend the analysis to negative masses, and they found a 3 sigma tension between cosmology and these lower bounds from neutrino oscillations. So we wanted to do this for all cosmological observables, so not just for the lensing effect of neutrinos, but also for the expansion history, and in principle also for clustering measurements. But it's not trivial to extend cosmological calculations to negative masses because it's not a physical thing. But so what I'm showing here is the fact that the Friedmann equations, they only depend on the neutrino masses squared. That's because it depends on the energy density, essentially, through expressions like this. But it's only at low redshift when this term A squared m squared over T squared, where T is the present day neutrino temperature, dominates, that the expression reduces to this well-known approximation where omega nu, so the density in neutrinos, is approximately equal to the sum of neutrino masses divided by some constant. But this dependence on the neutrino masses squared remains true at the perturbation level as well. And so we need to do it, we need to take a different approach if we want to extend our calculations to negative values. And the way we've done it now is by defining for any cosmological observable x, so for instance, these distance measurements from DESI or the CMB temperature power spectrum. And for some fixed set of parameters, which are these 6 parameters that are very well constrained by the CMB, we define the prediction for the effective neutrino mass, which can be positive or negative, as essentially first order expansion around the massless case. So we take the prediction for positive neutrino masses and then invert this to get the prediction for negative masses. And this is a very simple assumption that allows us to make predictions for all observables. And what you can see here are the distance measurements from DESI. So these are the black points. Then the gray dashed line is a massless lambda CDM cosmology. If we increase the neutrino mass, we get the blue lines. And so this is essentially decreasing H0, and it changes the distance measurements. And if we then extrapolate to negative values, we get the opposite. And you can already kind of see that this is going in the direction of these low redshift data points. So now we can go back to this Planck plot that I showed before and extend it to negative values. So here the gray area is the unphysical negative mass range. And we see that actually the CMB data allow for very negative masses with corresponding high values of H0 and high values of sigma 8. So by adding measurements of the expansion history, so for instance from shoes, from the local distance ladder, or from DESI BEO measurements, we can break this degeneracy between these parameters and get a tight constraint on the sum of neutrino masses, but now allowing for negative values. So here I've added the DESI BEO measurements, and we get a measurement of negative neutrino masses. So now we can go back to this posterior plot and extend it to negative values. And you can see here that for just Planck CMB measurements, it allows for very negative masses. But then adding the DESI BEO measurements and also CMB lensing measurements from both Planck and ACT, we get quite tight constraints, which are centered on minus 0.125 electrovolts. And this gives us a 2.8 sigma tension with the lower bound from neutrino oscillations, assuming the normal mass ordering. And if you assume the inverted mass ordering, it's a 3.3 sigma. So where is this signal coming from? A large part of it is from the CMB temperature power spectrum. So this is the famous plot of the CMB temperature power spectrum and the lambda CDM model that describes the data really well. But if we look at the residuals to this fit, there is some oscillation there. And this oscillation is responsible for this famous A-lens tension. But it can also be described by adopting lambda CDM with negative neutrino masses. And so, again, that's because essentially negative neutrino masses correspond to an enhancement of clustering and therefore a greater amount of lensing. And that's what the data seem to prefer. But it's not just coming from the CMB, but also from the DESI BEO measurements. So here I've shown a gray dashed line for a lambda CDM fit with physical neutrino masses, and then a best fitting model with negative neutrino masses. And it does improve the fit to these BEO measurements. So it's both CMB and BEO. So the first thing to try to solve this tension is to look at dark energy equation of state, because famously DESI has found these hints of a varying dark energy equation of state in terms of this W0 WA parameterization, where the equation of state W is a linear function of the scale factor, essentially. And so DESI has found a preference for varying dark energy equation of state between 2.5 sigma and 3.5 sigma when combined with Planck, ACT, and different supernova datasets. So let's redo this analysis, but with allowing for effective neutrino masses, which can be positive or negative. And what I should also say is there's a subset of W0 WA, which is the class of Mirage dark energy models. And these models are chosen in such a way that the distance to the CMB surface of last scattering is the same as it is in lambda CDM. And if you require that, you can impose this constraint between W0 and WA and get a one parameter extension of lambda CDM that still provides a really good fit to the data that I just mentioned. So it's those two models that we consider. And if we look at the posterior on the neutrino mass, we see that in these varying dark energy models, so the red line for W0, WA, and the blue line for Mirage dark energy, that the central value shifts significantly to the physical range. And the uncertainty is also slightly larger. But in this case, we get a marginal mean of 0.06 electrovolts for W0, WA, and 0.04 electrovolts for Mirage dark energy. And in this case, the data are fully consistent with neutrino oscillations. We can also look at the correlation between WA and some neutrino masses, and these are obviously correlated. And so this explains where this preference is coming from. Going back to the CMB temperature power spectrum and these residual oscillations, we see that the negative neutrino mass lambda CDM model and the varying dark energy models, they all describe these residual oscillations. And that's because they all predict additional clustering and additional lensing of the CMB. And they also all provide similar fits to the BEO data. And so that's why we described these negative neutrino masses as a mirage of dark energy. Of course, for the DESI, preference for varying dark energy was crucial to have the constraints from supernovae. And so here we've added the supernovae constraints as well. So the top line is just if you consider only Planck, ACT, and DESI, and then we have these three different supernova datasets. And the supernovae help to constrain H0, and so in the case of lambda CDM, they pull the neutrino mass to slightly more positive values, because H0 is constrained to be not as large as it would be without the supernovae. But in each case, there's still a 2 sigma or greater tension with neutrino oscillations. Whereas in the W0, WA model, the opposite happens. So constraining H0 actually pulls you to larger H0 values and correspondingly smaller neutrino masses. But in each case, the constraints are compatible with the lower bound for the normal mass ordering. It's the Mirage dark energy models that appear to perform best. And so they get tighter constraints on the sum of neutrino masses, and they're always compatible with neutrino oscillations. So that's the first part of the talk. Now I want to talk about the S8 tension. So S8 famously is this parameter combination of sigma 8, so the amplitude of matter clustering on 8 megaparsec scales, and square root of omega matter, the density in matter. And here I've added the constraint on sigma 8 from Kitts and Boss, so from the 3 times 2 point weak lensing and galaxy clustering analysis, showing that this analysis prefers lower values of S8 or sigma 8 compared to the Planck plus DESI analysis. So that's the S8 tension. And famously, baryonic feedback has a role to play here. So these are astrophysical feedback processes from supernovae and AGN that suppress matter clustering. And so this affects the weak lensing measurements in particular. And we can model this using cosmological hydrodynamical simulations. And there's many different suites out there that make different predictions. But we recently performed this very large suite of hydrodynamical simulations called Flamingo. And this is a picture of our flagship simulation, which is 2.8 gigaparsec in size. And it has 5,000 cubed baryon and dark matter particles. So this was a very expensive effort, but it allows us to model all these different astrophysical processes in a huge cosmological volume and make predictions for instance, weak lensing observations. And this is just to show that the Flamingo simulation, so the pink points are pushing the envelope in terms of resolution and volume. And we model many different processes in Flamingo, including neutrinos and decaying dark matter, as well as many variations in astrophysical feedback processes. One of the novelties of Flamingo is the way in which the many parameters that govern these astrophysical processes were chosen. And so this was done by training an emulator to predict different astrophysical observables, so the stellar mass function and the cluster gas fractions, as a function of all these subgrid parameters, and then fitting these parameters to the data in order to get constraints. But the crucial thing here is that this procedure was done at a fixed cosmology. And so I was interested in the question, what happens if we change cosmology? Do the cosmological parameters interact with these astrophysical parameters? So showing this parameter space of sigma 8 and omega matter, and the constraints from Planck, which are shown in blue, and from Kitt's cosmic shear in pink, as well as from the 3 times 2-point analysis in black. The question is, if we do the calibration at one point in the Planck cosmology, can we just apply that everywhere in this parameter space? Or do we need to recalibrate our model? So to do that, to answer that question, I sampled some points from the Planck constraints and assumed that the astrophysical parameters applied and see how do the predictions change. So that's shown here. So these are the predictions for the baryonic suppression of the matter power spectrum. And you can see that they differ at the several percent level at scales smaller than 1 h over megaparsec. And so this is telling us that if we want percent level accurate predictions of matter clustering, we need to take into account the coupling between baryonic feedback and cosmology. So what are the different mechanisms that could explain this coupling between feedback and cosmology? I thought of 4 possible explanations, one having to do with the binding energies of dark matter halos. So if you change the cosmology, you change the mass concentration relation, and in principle that could change the balance between outflows from astrophysical processes and the gravitational binding energy that wants to keep things clustered. Another possible explanation is the assembly history. So changing cosmology could change the formation times of halos and change when and how much feedback happens. The third possibility is the environment. So changing the large-scale environment through clustering could change how feedback impacts these results. And finally, the gas content. So changing omega baryon essentially changes how much gas is available for star formation and for these other gas processes. So look at taking this very large simulation of 2.8 gigaparsec, which has a huge number of clusters in it, we can see how different halo properties affect the amount of feedback that happens. So here I'm showing the effect. So this is the baryonic effect on halo mass, but then shown for groups with different amounts of halo concentration. And what it's showing is that there's 2 different regimes. In the low mass regime, the more concentrated halos are more strongly affected by feedback, whereas in the high mass regime, it's the opposite. It's the highly concentrated halos are least affected by feedback. And that's because there's 2 different mechanisms at play here. So for low mass halos, it's because of formation history. And so the formation history of halos famously is correlated with halo concentration. And here we see that the halos that form first have the most time to be affected by baryonic feedback. And so, but in the high mass range, the formation time actually doesn't matter anymore. And that's because once halos have accreted sufficient amount of mass, black holes become self-regulating, and they more or less attain a universal mass as a function of halo mass and concentration. So in the high mass range, it's actually the concentration itself. So it's the binding energy of the halo that governs how much feedback happens. And finally, we looked at the halo environment and found that actually this doesn't play much of a role. So going back to these 4 possible hypotheses, we could rule out 2 of them, the assembly history and the environment, and focus on the binding energies and the gas content of halos as being most important, governing the amount of feedback that happens. And so now we can look at how cosmology changes the binding energy and the gas content and understand the coupling between cosmology and baryonic feedback. So we developed this simple analytical model. I'll just quickly go through some of the assumptions. So one is that we can write the gravitational binding energy of the gas cloud as the binding of the gas to itself. And that's because in the center of the halo, the gravitational potential is initially dominated by baryons. And so the gravitational binding energy scales as the baryon fraction squared. And the second assumption is that black holes eventually become self-regulating, such that the energy injected into the gas is limited by the binding energy of the gas. And so we can relate the energy of the AGN to the gravitational binding energy. And we assume that we can write the velocity distribution of the hot gas as in terms of a scale variable Vg, which depends on the ratio of the energy of the AGN to the gas mass. So putting all of this together and using the fact that we can write the escape velocity of the halo in terms of Vmax, we can look at the fraction of gas that escapes, which is the fraction of the velocity distribution that exceeds the escape velocity, and write this in terms of this single variable psi, which is the ratio of the square root of the universal baryon fraction to the halo concentration. And yeah, putting all of this together, what it allows us to do is write the suppression of the matter power spectrum in terms of cosmological parameters, which is what we set out to do. So we can write the suppression of the power spectrum FB as a function of psi squared, which depends on the gas fraction, so omega baryon divided by omega baryon plus omega CDM, and this combination of omega matter and sigma 8. So to test some of our assumptions on the simulations, one of the assumptions was that we could relate the AGN energy to the gravitational binding energy and that it would scale as the baryon fraction squared. And that's exactly what is borne out by the simulations. And putting the complete model to the test, we see here how the change in baryonic feedback, the matter power spectrum, depends on this parameter psi squared. And we see that it provides a really good fit over a huge range of cosmologies. So going back to this parameter space of sigma 8 and omega matter, we can now use the model to predict where we can apply our calibrated model. So assuming we calibrated the model at a fiducial Planck cosmology, where can we faithfully apply it? And that's shown here by this red contour. So within this red contour, baryonic feedback behaves the same as it would in a Planck cosmology, but outside it's different. And interestingly, it's in the range of lower omega matter and lower sigma 8 where baryonic feedback gets stronger. So this is the really interesting thing, because if we try to solve the SA tension by introducing some new physics that either lowers the amount of clustering or lowers the matter density, then it also makes baryonic feedback stronger. And so these two could play together and help us solve the SA tension, essentially. So applying this to two such models. So one is allowing for a large neutrino mass. We just saw that actually neutrino mass is probably very small. But as an exercise, we can see what happens if we allow for a very large neutrino mass and see what happens to baryonic feedback. And in this case, we see that feedback indeed gets stronger. And that's because neutrinos, a large neutrino mass reduces the amount of clustering, and it also reduces omega matter, or at least omega CDM. And both of these effects increase the amount of feedback. And the second mechanism is decaying dark matter. So decaying dark matter behaves superficially similar to massive neutrinos in that it suppresses the amount of clustering and it reduces the matter density. And in this case, the coupling with baryonic feedback is very strong. So it exceeds 10% in the most extreme case. And so, yeah, if we're trying to solve the SA tension with new physics, this is a mechanism that should be taken into account. So I'll leave you with my conclusions. So first of all, if we relax the prior that the sum of neutrino masses should be positive and allow for an effective neutrino mass parameter that can be positive or negative, then we find a 3 sigma tension between lambda CDM cosmology from DESI, ACT, and Planck, and the lower bounds from neutrino oscillations. But if we allow for an evolving dark energy equation of states, then we can relax this tension and actually find positive neutrino masses. And in the second part of the talk, I talked about how baryonic feedback is cosmologically coupled and how feedback is stronger for models with reduced S8, such as models with massive neutrinos and decaying dark matter. And yeah, I'm very happy to take your questions.
Thank you so much. Any questions? Yeah, Sayantan.
Hi. So thank you for this very amazing talk. So I was just asking that you are suggesting the neutrino negative mass like globally or like locally? Like locally, you can always have a negative mass which spontaneously decays to something like whether it's tachyon or like k-essence field, etc. So I'm saying that how can global negative mass be stable? Like what would be the Lagrangian sign in the kinetic term itself? Like could you just explain that first?
Yeah, no, that's not, sir, if that's not what I'm suggesting. So I'm treating it as a phenomenological parameter to allow us to see where the data take us. So I'm not suggesting that the neutrino mass is negative either locally or globally, but rather that this is what we get if we assume lambda CDM, but the true underlying cosmology is something else. So yeah, that's what I was trying to say.
Thank you. Yeah, any other questions or comments?
Can I ask a small question another?
Yes.
Oh, okay. Yeah, I was just wondering that this is an amazing phenomenological work, but I am saying that from high energy point of view, I mean, does this have a implication of the say, mass problem in neutrino? Like, I mean, there are ways like if you can embed the SU5 into SO10 to give the neutrino mass, also the left-handed, I mean, needs to be destroyed. So I'm just wondering that is there a natural way to fit this into the say standard model to get the mass of the neutrino? Because as far I understand, the Marijuana, the double BK experiment is not showing that it is a marijuana neutrino. So could you just comment on that if you can? Thank you, sir.
Yes. So yeah, I don't know how it fits in with the nanograph finding. Yes, so I'm sorry. Yeah, I've treated this as a phenomenological parameter. Yes.
Thank you, sir.
Thank you. Erwin?
Hey, well, you can hear me, right? Everybody
Yes,
hear me?
I can hear you.
Okay. Thanks for the talk. So the first is that there's a comment in the chat, and it's basically that, you know, as W0 goes up, H0 goes down. So if we look at DESI results, basically we're still 4 sigma away from Adam's determination of H0.
That's right.
Now,
yes.
if you relax the sum of the neutrino masses, either in W0, WA or the Mirage model, how far away are you from shoes in terms of sigma?
Yes, that's
That's the first question. The second question is, why do cosmologists believe that SA tension can be decoupled from H0 tension? That's the second question.
Right. So to answer your first, yes, thank you. To answer your first question, so for the Mirage models, actually we hit the same H0 as that you would get for lambda CDM with the physical neutrino masses. So it's still in the 66 to 68 kilometers per second per megaparsec range. So we don't at all solve the H0 tension here. So that's to answer your first question.
Right. And now H0. Why are S8 and H0 not related?
Because they're really, you know, they're I think they are related, frankly, but the measurements are completely different, right? So we're just comparing different kinds of measurements. When you're trying to solve them, I think you can't avoid the fact that these parameters are correlated in lambda CDM.
Right. So I think what I'm getting at is basically that, you know, there's probably something wrong at the background level, right, that you need to address. And viewing S8 as a perturbative problem, you know, I mean, there's lots of things you can do perturbatively that would sort of leave the background intact as lambda CDM or something close to lambda CDM, but you're not going to be able to resolve H0 tension that way. That's more or less the gist.
Yes, yeah, and right. That's indeed a further difference between the two. One is purely a background measurement, and the other one involves clustering.
Right.
Yes.
Thanks.
Thank you. Adam?
Willem, very nice talk, very interesting. You know, I could certainly imagine people saying, oh, this, you know, negative neutrino mass, this is silly, this is you know, it's unphysical, okay, phenomenological, but there's no physics, so I'm not happy. But I think you were pointing out, and maybe this is something I hadn't appreciated, we're already unhappy with neutrino masses because with the latest data, they move below either the normal or inverted hierarchy. So nobody could be too happy in the neutrino mass world at the moment anyway, yeah?
That's right, yes. And it's kind of explaining why the data prefers such low values. Right? It's because lambda CDM prefers a negative neutrino mass that we get these very tight upper bounds, even if you impose a prior that it should be positive.
Interesting. Thank you.
And it's by allowing it to be negative that we can actually reveal this shift between lambda CDM and W0 WA CDM. So I think it's a useful exercise to see where the data take us for particular models.
And are the plots you're showing, are they from a particular paper?
Yeah, so it's a paper we put out 2 days ago, so it's on the archive.
Awesome.
Let me get, yeah, so it's the number at the bottom here.
Thank you.
Thank you so much. Any other questions? Osgur?
Hello. So my computer is very slow. I don't know if my voice is coming fluently or not.
I can hear you, yes.
Okay. So you know, if for one of the solutions for H0 tension is that in case you have negative dark energies and negative dark energy densities for redshifts values like larger than 1.5, we can increase H0 to the shoes measurement. So I mean, and there are some indications in the data sets you use towards negative dark energies I at high redshifts. My point is this: we recently submitted a paper to archive where we compare lambda CDM and lambda CDM. So lambda CDM is a model where you have ADS vacuum energy for large redshifts, but at low redshifts you have positive cosmological constant. For Z values like larger than 0.6, you have negative cosmological constant. In that case, we are able to address H0 tension, S8 tension, and several other tensions. So recently, we studied lambda CDM at this model by allowing an effective to be free parameter and neutrino mass to be free parameter. What we observed is that when we allow an effective and neutrino mass to free parameter, on top of standard model, we were getting neutrino mass an effective like 3.5, and neutrino mass is less than 0.06 EV. That was interesting for me. But when we had negative cosmological constant at high redshifts, we were recovering standard model values, an effective 3.044, and neutrino mass is consistent with local observations. I mean, so neutrino mixing observations. So this point we wrote in our paper. So, and now I'm seeing your figures. For instance, you recovered proper values for neutrino mass when you use CPL parameterization, but when you have large negative values of equation of state parameter at high redshifts, right? So it is like a phantom field, right?
That's right, yes.
So the point is this. So this is a typical behavior for if you want to have a dark energy changing sign. Just after changing sign, you should have large negative values for the equation of state parameter. This is because of continuity equation. So because what happens is this dark energy density is decreasing quickly with increasing Z, right? So that is why you are recovering this positive values for neutrino mass. My point is this. So CPL is a parameterization to equation of state parameter. So would you think of doing such a work by considering negative dark energy values at high redshifts? I believe in that case, so this problem will disappear. So because this phantom behavior is decreasing energy density of dark energy with increasing redshift, but the minimum of phantom dark energy is 0, right? But if you have negative dark energy at high redshifts, it will be even less than 0. So this can help with addressing H0 tension, S8 tension, and without any problem with ineffective and neutrinos, I guess. So all these things make sense to you? So I don't know. I mean, so I wanted to make a comment.
Yes,
Question by saying like this. Sorry. Okay.
Okay, very interesting. Yes, I haven't considered negative dark energy densities here. And I should say in this plot, if we include supernovae data, then the constraints shrink a lot. And so we don't get such large negative values of WA. But if I understood correctly, you were saying by allowing for a negative dark energy density at high redshift, you recovered a physical neutrino mass and physical
Yes.
standard model prediction for N effective. Is that right?
Along with H0, consistent with Schu's measurement and without S8 tension. So can you please open your last figure in your talk, this where there are some error bars? In your slides, can you please show the last figure of yours?
Sorry, I didn't catch the last part.
Can you please open your last figure?
Oh, my last figure?
Yeah.
Oh, you mean the previous one, this one?
No, the last one. I think error bars were there. Okay. This one. Okay, this one. You see what I see is here, when you use Pantheon Plus, this problem is more emphasized, right? So you have this error bars are in the gray region where you have negative mass, right?
Yes.
So there are some indications in Pantheon Plus data that it prefers like negative energy densities are for redshifts larger than 1.5. So these seem like in case you consider in your analysis possibility of negative dark energy densities at high redshifts, it seems that you could get even better results. So yeah, I want to comment on this one.
I would be pleased if you could send your paper to me.
Okay.
Thank you. Any other questions or comments? No? So let's thank Willem again. Thank you so much.